Hello, everybody. Welcome to the February 15th class. We're going to do this on video today because of the horribly cold weather out there. Hope you guys are staying warm. We are going to go over just a little bit here. I want to go over a little bit more about allylic halogenation, and then we'll do one more new concept, and then practice a couple of synthesis questions. All right, so first of all, let's do another problem relating to allylic halogenation. We've done several examples on that so far. I want to show you this one that looks seemingly pretty simple. And forgive me, I do not have a stylus today, so I am drawing with my fingers. And that might get a little bit clumsy here at times, but I think it'll be okay. All right, so let's say we have this alkene. All right, and we're going to react it with NBS and heat. All right, so of course you guys know by now that if you see NBS pop up with an alkene, you're going to be definitely doing an allylic halogenation. All right, so as always, with radical mechanisms, our first step is initiation. So just to remind you, this is what NBS looks like. All right, and of course, we're going to break this apart into radicals. So we have that one, which we don't care about. And more importantly, we have that Br radical. All right. So once we form that Br radical in the initiation step, then we're actually ready to use it in propagation. And this is where our hydrocarbon comes in. Okay. Now, we've done this a couple of times before, and so, hopefully by now you're used to the fact that, when you take a look at this, you're going to be looking for, first of all, allylic hydrogens, right? Okay. Sometimes we only have one allylic spot, right? Other times we might have a couple of allylic spots, but one of them produces a more stable radical, right? So there might be a preference. We saw an example of that, I think, at the very end of class the other day. This one's interesting, though, because we have two allylic spots here and here. And if you look, this is not a symmetrical molecule, so they're not identical. And there is actually, so they're not identical, but they do produce the same types of radicals, right? You have a couple of different possibilities. Remember, whenever you conduct this propagation step, what you do is you have the Br radical abstracting an H radical from your allyl position. If you did this, you would get this particular radical, right? Well, we have another allylic spot. We have another allylic hydrogen that we could possibly take, one right over here. All right, now if we did that, we would end up with that radical. And interesting thing about this one, both of these radicals are secondary allyl radicals, right? They're both secondary allyl, so they have the same stability, although they are not exactly identical, right? On the left-hand side, your carbon radical has a methyl attached to it. On the right-hand side, your carbon radical has an ethyl group attached to it. All right, so which one of these forms? Is there a preference? Well, this is going to be a case where, unfortunately, you get both. And so you have to work off of both since they have equal stabilities. Okay? So, let's see. I'm going to, since unfortunately I don't have that much space on here, I'm going to come back to this one. I'm going to work off of this one first, show you the products, and then move on from there. So this radical could then interact with a Br2. Where did we get the Br2? From termination, absolutely, right? All right, so you can have this radical breaking apart your Br2 and giving you this. And this would be, whoops, again, I'm doing this with my fingers, so bear with me. All right, this would give you this constitutional isomer, right? You may notice that this has also produced a new stereogenic center, so this would actually exist as a racemate. All right, so that would be one set of products right over there. However, don't forget, what did we see with allyl radicals? Resonance. Instead of breaking apart right here, so instead of having this particular radical break Br2, you could have had a resonance form in which, and I'm going to erase this just so I can show it to you without having to draw everything over. You could have had this bond right here break apart. Whoops, crap. You could have had this bond break apart. One electron pair up with the other radical that was formed, and one electron move over there to form an alternate resonance structure. And then that resonance structure could have reacted with Br2 to give you this particular constitutional isomer, which again would exist as a racemate, having to break it up just because of space limitations. And in both cases, you would get Br radical as a side product here that could continue the propagation. All right. So yeah, whenever you're looking at these allylic halogenations, definitely do it step by step. Look to, number one, look to see how many unique allyl spots there are. Draw the possibilities for radicals, right? If one of them's like a primary allyl, the other one's a secondary allyl, you would only go through the secondary allyl. However, in a case like this, where you make two similar types, secondary allyl, then you have to proceed through both of them and make the appropriate products. All right. So we showed one set of products here. All right. I'm going to erase this, and we're still, working on the same problem, same propagation step. We're going to work off of the other radical, right? That we could have formed. We're going to work off of this one. All right. Now, again, just like with the other radical, you could have either just had a direct reaction with Br2, to form this. All right. Again, this would be a racemate. Wow, so you see, if you include all stereoisomers, we're up to 6 products already. That's fun. Okay. And then you have to account for possible resonance that would occur. All right, so what we would do, we would split this electron up. Let's split this bond up into electrons, like this. Draw a resonance structure. And we get that. And then that could react with Br2 to make this. Okay. Now, in this particular case, you'll notice that this structure is identical to the one you did to the product you got with the other resonance structure. So this one actually does not give you anything unique. Unfortunately, there's really no way to predict this before you actually go through the mechanism and work the problem. So in a case like this, going back to the very beginning of the problem, you see that you could make two different allyl radicals. All right, select one of them, draw a product with each resonance structure, see what you get. Take the other one, draw a product with each resonance structure, see what you get. Sometimes you'll get duplicates, sometimes you won't. All right, so you just make sure to include any unique products in your final answer. Okay? All right. This is like I said, this was sort of a simple looking one that was actually a bit more complicated, and that's the way it does sometimes, but that's an example of one of the more complicated types of these types of problems. Okay. All right, so that's radical addition to radical halogenation of an allyl carbon. We're going to shift gears now. Now, we're going to do radical addition. Wow, that's really sloppy handwriting, I know, like a kindergartner. Of HBr to an alkene, right, to a carbon-carbon double bond. So this is a little bit different. And it's also going to be a little bit different than what we've learned previously. We've learned how to, add HBr to a double bond, right? If you guys remember, let's see, take a look at this example, right? We could take this alkene, terminal alkene, HBr, and I'll walk you through the mechanism. You guys have done it before. We did it in the alkenes chapter, right? You know that the pi bond accepts an H+, and we follow Markovnikov's rule. Them that has gets, this carbon has more hydrogen, so it's going to get this hydrogen as well, and it does that to make the most stable carbocation. And then the Br minus comes in right there, boom, and you have your addition of HBr. That's what we've done in the past, right? And so in this case, you see the Br goes to the middle carbon, you get 2-bromobutane. However, there's a way for us to get an anti-Markovnikov addition. It's possible for us to go from this to this. All right? Does not follow Markovnikov's rule. Reason it doesn't follow Markovnikov's rule is because we're not even going to end up making carbocations. We're going to do a radical process. All right? So it's pretty similar. However, you have to add more stuff to it. And instead of just adding HBr, you're also going to add a peroxide. And I'm going to represent peroxide here, ROOR. And then an energy source, either heat or UV light. All right? All right, let's see how this is going to proceed. All right? Just like anything else radical, you're going to have initiation, propagation, termination. All right, initiation. First of all, we got to make the radicals, right? And it all starts with the peroxide because peroxides, as I've mentioned, have very unstable oxygen-oxygen single bonds, right? And that's where we're going to form our radicals. So you're going to have a peroxide. We're going to have our energy source. We'll use heat in this case. And that is just simply going to cause that OO single bond to break up. And voila, we've got two initiator radicals, RO radicals. All right. There is one more step in initiation. You're going to take one of those RO radicals, and it's going to react with your HBr. All right. It is just very simply going to abstract a hydrogen radical, right? So it's going to grab on, whoops, single-headed arrow, sorry. It's going to grab onto an H radical to form an alcohol, which we don't care about anymore. But more importantly, it's going to form a Br radical. That's what we want. So this is a little bit unique. This is the first initiation stage that you've got looked at in any of these mechanisms that has more than one step. All right, it's the only one out of the, I think, 3 or so that we've learned. All right, so you form the peroxide radical. Peroxide radical abstracts an H radical from HBr, and then boom, you got your Br radical, and you are ready to rock and roll with your alkene. And we are ready to proceed into propagation. All right, so propagation, we're going to have our alkene, and we're going to have our Br radical. All right, so what that Br radical can do is it can directly add to one of the carbons in the double bond by splitting the pi bond apart. All right, so there's a couple of different possibilities. You could have this happen, where the Br attaches to this carbon and leaves a radical right over here. Okay? Or it could happen the other way, where the Br radical, come on, there we go, where the Br radical adds to this carbon and you form a radical in the middle. So, again, the question we always have to ask ourselves in situations like this, is one of these preferred, or do they both occur, right? Well, let's look and see what type of radicals we made in each case. On the left-hand side, we have this radical on an end carbon. That's a primary radical. Over here, this is a secondary radical. Well, we know bromination is always selective, so we're going to proceed through the most stable one, and that means that we only go through this guy right over here. Okay? So, first step of propagation in this case, and I'm going to redraw it kind of a little bit neater. Is we're going to have the Br on the end. So you can see this is where the anti-Markovnikov portion of this comes in, because it makes a more stable radical. Okay? Then, once you make that, it can interact with another HBr, all right? And your carbon radical can simply abstract an H radical to give you your product, and then another Br radical that can keep pushing things along. Okay? And then termination, as always, is just coupling of combinations of various types of radicals. All right. Instinctively, I want to say any questions, because that's kind of my thing I do. But then I remember that, hey, I'm not in there, so you guys can ask me. But as always, if you have any questions, be sure to ask me. I'll be happy to clarify anything that needs clarifying. All right? Very good. Let's try another one. Let's extend that carbon chain a little bit. And we'll put double bond in the middle. All right. Now, I'm not going to go through the whole mechanism of this one. Hopefully you should be able to follow the model that I employed in the last example. It works the same. All right. The only difference here is you have a couple of options. All right. At some point In initiation, we're going to form the initiator radical, which will then react with HBr to form a Br radical, right? And then the Br has to add to the double bond, right? So again, just like we did last time, let's take a look at the possibilities. The Br radical could break your double bond and add there, leaving that radical, or it could have done so on the other carbon. All right? So those are the two radical possibilities. Now, in the last problem we saw, one of them was definitely easier to form than the other one. One of them was secondary, one of them was primary. This case, though, it's a little bit different. They are both secondary radicals. So guess what that means? You have to work off of both of them. That's right. So this would be a case where you get more of a mixture of products. Again, I'm not going to work the whole mechanism. You guys know how to do this now. But if you have any questions on it, let me know. Eventually, this would lead to formation of this product and the formation of this product, which is a racemate. The top one doesn't have a stereogenic center, so you don't have to worry about it there. But yeah, we would get a mixture of those products. Okay? All right, let me try one more with you. Again, I'm just going to tweak this a little bit. I'm going to add a methyl group. All right. Now, again, same process. Eventually you're going to get to a point where you have this and a Br radical. The Br's got to add to the double bond in some form. So again, let's draw the possible radicals. The Br could add itself there and make a radical on that carbon, or it could add itself here and put a radical on that carbon. Okay? Again, so just like we've been doing, compare the radicals. All right? In this particular case, I think we can see that this one is tertiary, whilst this one is secondary, right? So this is nice because we can definitely see that this one is the preferred radical. Yeah, and if you keep on with the mechanism, you would see that this would be your product. All right. Hopefully that gives you a pretty clear picture of what's going to be happening with these radical additions to double bonds, and then prior to that, the allylic halogenations. That is pretty much it as far as the radical halogenation reactions that we're going to see. There is another set of reactions in this chapter that I'm going to go over with you, but just not in this video. I'll wait till we get in person. Those are going to be free radical polymerizations. And they're very similar to what we've been doing, but they're also definitely a bit different too. So I want to talk about those in class. One thing I will do before I sign off is I want to do a couple of practice synthesis problems. Everybody's favorite. Of course, we're adding radical mechanisms here, so that's going to increase the range and versatility of our, I have the hiccups, synthetic offerings. All right? I think it actually makes life a bit simpler because it makes the possibilities a lot more versatile. All right? So, for example, let's try this one. I'm going to do a couple of them with you. Let's say we're trying to take cyclohexane and we're wanting to convert it into cyclohexene. All right? Now, this is a two-step synthesis. It's a pretty quick and efficient synthesis. Again, when you're looking at this, try to pick up any clues that you can from what you're given. One thing you may notice is that you have an alkane. You're starting off with cyclohexane. If you think back to everything that we've done this year, I don't think you'll be able to think of very many reactions that we can do with alkanes. In fact, there's only two. The first type of reaction with alkanes we learned way back in chapter 4, and that was just simply combustion. That was burning it, right? You can take an alkane, combust it with oxygen, burn it, make carbon dioxide and water. I think you can probably tell that's not going to be very useful here, right? The other type we just learned. The other type is radical halogenation. So if you're ever starting off with an alkane, chances are your first step is going to be a halogenation, because really there's not anything else that you can do with it but a halogenation. So that's where I would start here. I would do a halogenation. Bromination's usually the safe bet. In this case, I could use either bromination or chlorination, but I'm just going to use bromination. All right, if I do that, that's a terrible hexagon. I'm going to redraw it. All right, that allows us to put a Br in place of one of the H's. Okay? So now we have an alkyl bromide. All right, and we have learned how to make alkenes out of alkyl bromides. That's the organic 1 material. Right? To do that, we just need a good old E2 reaction. A strong base. I'll just use tert butoxide. Wow, this looks really sloppy with my finger. I apologize. I'm going to try to make a better effort. And then a solvent to go with it. Yeah. Voila. That is it. All right. So yeah, that's a really good that's a good hint to have in your mind. If you start off with an alkane, you're probably going to have to do a halogenation. Now, it's not the only time you can do halogenations. You know, you can certainly do them in the middle of a synthesis too, in certain cases. So don't think that's the only application, but it is one you'll see frequently. All right, let's do one more, and then I'm going to wrap it up. This one's a little bit more involved. All right, we're going to start off with cyclopentane, and we're going to convert it into this. All right. All right, so again, I mean, we're starting off with an alkane. There's really not much that we can do with alkanes but halogenate them. So let's try a halogenation. And that gives us a bromocyclopentane. Okay, so now I'm going to look and see, okay, I got to get from here to that final product. I'll tell you that overall, from this, the entire synthesis is going to be about 4 steps, so we should need 3 more steps. All right, looking at hints here. All right, I'm going to sort of go back to the end. Look at where this OH group is. That OH group is in a very particular spot. It's right next to the double bond, right? Which means it's in the allylic position. Now, we don't know any way of putting an OH in an allyl position directly, but we know we could have made this group through just a simple nucleophilic substitution, right? Good old chapter 7 stuff. If maybe we had an alkyl bromide. Ah, crud. So much easier with a stylus. There we go. Yeah, this is just a chapter 7 reaction. So, if we could somehow make this species that has a Br at an allyl position, that would be great. Well, we've done that before. We know how to make an allylic, we know how to do an allylic bromination. We know that if we had NBS in heat, for example, reacting it with an alkene, yeah, we can absolutely target an allele position and put a BR there. So basically you have two ends of the synthesis completed. Now you just have to link them. And again, just like we did last time, we can just do a good old E2 reaction here from last semester to make that. So voila, 4 steps. All right. So again, keep practicing, keep looking for these little clues, connect the dots. All right. I'm going to sign off there. We will pick up at this point on Wednesday. And first we will have a quiz, and then we will pick up and finish off this chapter. All right. Hope you guys have a great day. Bye-bye.